A Zener diode is a special type of semiconductor diode that is designed to allow current to flow in the reverse direction once a certain reverse voltage is reached. It has two key regions on its IV curve. Forward bias region behaves like a normal diode conducting after about 0.6 to 0.7 volts. Reverse breakdown region. When the reverse voltage reaches a predefined value, the Zener voltage, a controlled avalanche of carriers occurs, and the diode conducts heavily while keeping the voltage across it almost constant. The breakdown can happen by two mechanisms. Zener breakdown, dominant for Vz less than 5 volts, is caused by quantum tunneling of electrons across a very thin depletion layer. Think of it as water forcing its way through a narrow crack when pressure is high enough. Avalanche breakdown, dominant for Vz greater than 5 volts, is like a line of falling dominoes. One high-energy electron collides with the crystal lattice, creates additional electron-hole pairs, and the process multiplies. Both mechanisms are deliberately engineered to be reproducible, so the voltage at which they start, the Zener voltage Vz, is stable over a wide range of current. The key characteristic is the sharp knee in the reverse IV curve. After the knee, a small increase in current causes only a tiny increase in voltage, which is why Zener diodes are useful as voltage references and regulators. Explanation: when a Zener diode is connected reverse biased, cathode to the positive side of the circuit, anode to the negative side, it normally blocks current. As the reverse voltage rises, the diode stays non-conducting until the voltage reaches the Zener voltage Vz. At this point, the breakdown mechanism kicks in, and the diode starts to conduct a sizable reverse current, but the voltage across it stays very close to Vz. For example, a 5.6-volt Zener will hold the voltage at about 5.6 volts, even if the reverse current changes from 5 microamps to 50 microamps. The tiny change in voltage is called the dynamic resistance Rz and is typically a few ohms. An everyday analogy: imagine a water pipe that has a pressure relief valve set to open at 5 psi. Below 5 psi, the valve stays shut, no flow. Once the pressure reaches 5 psi, the valve opens and lets water flow, but it keeps the pressure at roughly 5 psi regardless of how much water is trying to push through. The Zener diode does the same for voltage. Mathematically, for V sub R less than Vz, I sub R approximately 0. For V sub R greater than or equal to Vz, I sub R equals open parenthesis V sub R minus V sub Z close parenthesis, divided by R sub Z, where R sub Z is the small signal dynamic resistance of the diode. Explanation: a basic Zener voltage regulator consists of 3 parts. Input supply Vs, the raw voltage that may vary over a wide range. Series resistor Rs limits the current flowing into the Zener and the load. Zener diode Vz, placed in reverse bias across the load to clamp the voltage. The circuit looks like a simple voltage divider, but the Zener diode forces its lower leg to stay at Vz. The series resistor does the heavy lifting. It drops the excess voltage, Vs minus Vz, and provides the necessary current for both the Zener and the load. Design steps: choose a Zener voltage close to the desired regulated output. Determine the minimum Zener current, Iz min, needed to keep the diode in breakdown, usually a few milliamps. Estimate the maximum load current, IL max. Compute Rs so that at the lowest acceptable supply voltage, the Zener still receives Iz min while delivering IL max. The regulator works like a pressure regulator on a gas line. The Zener is the pressure setting spring, and the series resistor is the throttling valve that supplies enough gas to maintain that pressure even when downstream demand changes. The key equation for the series resistor is Rs equals open fraction Vs minus Vz over Iz min plus IL max close fraction, where Vs is the worst case, minimum supply voltage that the regulator must handle. Numerical example: suppose we need a 12-volt regulated output for a circuit that draws up to 200 milliamps. The available supply varies between 15 volts minimum and 18 volts maximum. We select a 12-volt Zener with Iz minimum equals 5 milliamps. Calculate total current needed at the lowest supply voltage. I total equals IL max plus Iz min equals 0.200 amperes plus 0.005 amperes equals 0.205 amperes. Find RS using the minimum supply voltage 15 volts. RS equals open parenthesis Vs min minus Vz close parenthesis, divided by I total equals open parenthesis, 15 volts minus 12 volts close parenthesis, divided by 0.205 amperes. RS equals 3 volts divided by 0.205 amperes, approximately equals 14.63 ohms. Choose a standard resistor value of 15 ohms, preferably with a power rating of at least 0.5 watts. Check Zener current at maximum supply 18 volts and minimum load 0 amperes. The current through RS at 18 volts. IS max equals open parenthesis Vs max minus Vz close parenthesis, divided by RS equals open parenthesis 18 minus 12 close parenthesis, divided by 15 equals 0.4 amperes. If the load draws nothing, the entire 0.4 amperes flows through the Zener, which may exceed its rating. Therefore, we add a maximum Zener current limit by choosing a Zener that can handle at least 0.4 amperes, or by adding a second resistor parallel Zener. In practice, we would select a Zener with a power rating of at least Pz equals Vz times Iz max equals 12 volts times 0.4 amperes equals 4.8 watts, or redesign the regulator using a larger RS. This example shows how the series resistor is sized, and why checking both extremes of supply and load is essential. Load regulation is the ability of the regulator to keep the output voltage constant as the load current changes. It is expressed as load regulation equals delta V out divided by delta IL in volts per ampere, or as a percentage. Percent regulation equals V no load minus V full load divided by V full load times 100%. In a Zener regulator, load regulation is mainly affected by the dynamic resistance of the Zener R sub Z. A higher R sub Z causes a larger voltage drop when the Zener current changes. The series resistor RS, if RS is large, a change in load current causes a noticeable change in voltage drop across RS, adding to the output variation. Effect of varying load currents. When the load draws more current, less current is left for the Zener. Iz equals Is minus IL. Because Iz falls, the Zener voltage drops by delta V sub Z equals R sub Z delta I sub Z. Simultaneously, the voltage across RS changes by delta V sub RS equals R sub S delta IL. The total output voltage change is the sum of these two drops. Example using the previous circuit with RS equals 15 ohms and a Zener whose R sub Z equals 5 ohms. Suppose the load current goes from 0 amperes to 0.2 amperes. Voltage drop across RS changes by delta V sub RS equals 15 ohms times 0.2 amperes equals 3 volts. Zener current reduces by 0.2 amperes, so delta V sub Z equals 5 ohms times negative 0.2 amperes equals negative 1 volt. Net output change delta V out equals negative delta V sub RS plus delta V sub Z equals negative 3 minus 1 equals negative 2 volts. Thus the output falls from 12 volts to about 10 volts, indicating poor regulation. To improve it, we would lower RS, use a higher supply voltage, or select a Zener with a smaller R sub Z. Regulation percentage in this case. Percent regulation equals 12 minus 10 divided by 10 times 100%. A good regulator aims for less than 1% variation. From this explanation, you just need to break them into segments, and for each segment return phonetic reading style of the segment. Explanation. When the Zener diode conducts in reverse breakdown, it dissipates power equal to the product of its voltage and the current flowing through it. P sub Z equals V sub Z times I sub Z. The diode's thermal rating, usually given in watts, tells us the maximum power it can safely dissipate without overheating. Exceeding this rating can cause the junction temperature to rise above the safe limit, leading to drift in V sub Z or permanent damage. Example calculation. Assume a 5.6 volt Zener rated for 0.5 watt. The maximum allowable Zener current is I sub Z max equals P max divided by V sub Z equals 0.5 watts divided by 5.6 volts, approximately 89 milliamps. If our regulator is designed with R sub S equals 100 ohms, and the supply voltage can rise to 12 volts. The current through R sub S at maximum supply is I sub S max equals 12 minus 5.6 divided by 100 equals 0.064 amperes, which is 64 milliamps. If the load draws 0 amps, all 64 milliamps flows through the Zener, which is below the 89 milliamps limit, so the diode stays within its rating. However, we must also consider junction temperature rise. Delta T equals P sub Z times R theta JA. Where R theta JA equals 200 degrees Celsius per watt, then at 0.5 watt the temperature rise is 100 degrees Celsius. Adding a heatsink reduces R theta JA and keeps the temperature within safe limits. Practical tip: always design with a safety margin. For example, keep P sub Z less than or equal to 50% of the rating and provide adequate airflow or heat sinking. The dynamic or small signal resistance of a Zener, denoted R sub Z, is the slope of the IV curve in the breakdown region. R sub Z equals delta V divided by delta I, evaluated at V approximately V sub Z. It is typically a few ohms for low voltage Zeners and can be less than 1 ohm for high power devices. This resistance acts like a tiny series resistor inside the Zener and directly impacts regulation accuracy. How R sub Z influences regulation? When the load current changes, the Zener current changes by the same amount but opposite sign. The resulting voltage shift across the Zener is delta V sub Z equals R sub Z times delta I sub Z. If R sub Z is large, even a small change in current causes a noticeable voltage change, degrading regulation. Conversely, a small R sub Z keeps the Zener voltage almost constant. Design implication: to achieve a desired regulation, plus or minus 0.5% of V sub Z, the allowable Zener current variation delta I sub Z is limited by delta I sub Z is less than or equal to plus or minus 0.005 V sub Z divided by R sub Z. For a 12-volt Zener with R sub Z equals 2 ohms, the permissible current swing is delta I sub Z is less than or equal to 0.06 volts divided by 2 ohms equals 30 milliamps. Thus the series resistor and supply must be chosen so that the Zener current never varies by more than plus or minus 30 milliamps over the expected load range. In practice, designers often select Zeners with low R sub Z or use series parallel Zener arrays when tight voltage tolerance is required, such as in precision reference circuits or a DC front ends. 1. Design problems. Given a 24-volt direct current supply that may vary between 22 volts and 26 volts, must provide a regulated 15 volts to a load that draws 100 milliamps to 300 milliamps. Choose a 15-volt Zener rated at 0.5 watts and calculate the value of the series resistor. Show the worst-case Zener current at both supply extremes and verify that the Zener stays within its power rating. Compute I sub L max equals 0.3 amps, I sub Z min from the Zener's knee, for example 5 microamps. Use the lowest supply 22 volts to find R sub S equals open parenthesis 22 minus 15 close parenthesis divided by open parenthesis 0.3 plus 0.005 close parenthesis approximately 22.6 ohms, then choose 22 ohms. Then find I sub Z at 26 volts with no load. I sub Z equals open parenthesis 26 minus 15 close parenthesis divided by 22, approximately 0.5 amps. Then power P sub Z equals 15 times 0.5 equals 7.5 watts, which exceeds the rating, so a higher power Zener or an additional series resistor is needed. 2. Conceptual question. Explain why a Zener diode with a larger Zener voltage, for example 12 volts, typically exhibits avalanche breakdown, whereas a 3.3-volt Zener uses the Zener tunneling mechanism. Discuss how the two mechanisms affect the temperature coefficient. Zener tunneling dominates in narrow depletion regions, high doping, giving a negative temperature coefficient, meaning the voltage decreases with temperature. Avalanche breakdown involves carrier multiplication, giving a positive temperature coefficient. Therefore, low-voltage Zeners tend to have a negative temperature coefficient, high-voltage ones a positive temperature coefficient. 3. Numerical regulation. A Zener regulator uses R sub S equals 470 ohms, V sub Z equals 6.2 volts, and the Zener has R sub Z equals 4 ohms. If the load current changes from 0 milliamps to 10 milliamps, calculate the change in output voltage and the regulation percentage. Delta V sub Rs equals 470 times 0.01 equals 4.7 volts. Zener current drops by 10 milliamps, so delta V sub Z equals 4 times minus 0.01 equals minus 0.04 volts. Net delta V out equals minus open parenthesis 4.7 minus 0.04 close parenthesis equals minus 4.66 volts. Output goes from 6.2 volts to approximately 1.54 volts. Percentage regulation equals open parenthesis 6.2 minus 1.54 close parenthesis divided by 1.54 times 100, approximately 302%, which is very poor. This shows the need for a smaller series resistor or a larger supply. 4 is thermal ratings. A 5-volt Zener with P max equals 1 watt is used in a regulator that supplies 50 milliamps to the load. The supply is 9 volts and R sub S equals 80 ohms. Determine the Zener current and its dissipated power. Is the Zener within its rating? Assume the load draws its maximum current. Total current I sub S equals open parenthesis 9 minus 5 close parenthesis divided by 80 equals 0.05 amps. Load draws 0.05 amps, leaving I sub Z equals 0, so the Zener is off and power is 0 watts, which is safe. If the load drops to 0 amps, I sub Z equals 0.05 amps, power P sub Z equals 5 times 0.05 equals 0.25 watts, which is less than 1 watt, also safe. These questions test understanding of sizing series resistors, checking power limits, knowing breakdown mechanisms, and quantifying regulation effects.